Okay, so hello everyone. Thank you for being here and for listening to me. So okay, so we are here today to present you a test solution provided by Siemens, which is really interesting, and it's defect-oriented that aims to cover bridge and open defects. And we wanted to do some trials with this solution in order to improve our test quality. And also, we always seek, for new test solutions in order to provide the best coverage, especially for our automotive customers. So that's the main reason we did. We wanted to try this solution. Okay. So I will start by presenting a bit the imaging division in which I work, the DFT and engineering team. The selected device, because I'm not at liberty of saying the name, which is a very beautiful name, but whatever, that we did the trials on. And then we're going to go over the bridge and open solution flow. And then we're going to end by presenting a few the diagnoses we did. We tried to collect as many as data as possible. And then in conclusion with the next steps, because please keep in mind that the tests are still ongoing. So we gathered as much as possible data, but it's not over yet. Okay, so Imaging Division is a division of STMicroelectronics where we work of custom mixed sensors and time of flights. With very different technologies, and we're the application is various, and in many fields we really target the automotive especially, and the consumer products as well, the consumer market. And the sensor that we're going to see today is really targeting the consumer market. Okay, so the DFT team inside of Imaging is a bit different than the other DFTs, I guess, because we're a part of engineering, and we do design for tests, but we do design for electrical characterization, and we do design for manufacturing as well. And the thing is that the DFT, our team, is multidisciplinary, sorry, and we actually work on scan patterns, verification, functional and structural verification. And what we do in addition of that is working on custom BISTs. So that means that we develop and we specify and we design IPs that are BISTs, basically, to cover the analog, which is unfortunately not covered yet by the scan. Okay, and for that we chose one of our sensors, and it's a 3D, it's a global shutter 3D that targets some of the consumer markets, which are which are basically depth sensing for that would be gesture sensing, distance measuring. Distance sensing, area, room sensing, for example, like room scanning, biometrics for iris recognitions, augmented reality, virtual reality. The applications are really various. And so the point was really to evaluate the ratio, cost, and performance of this test solution on one of our most mature sensors, because this is really a mature sensor. We know this product, we know the defects that we could have, we know the data that we could expect. So we wanted to test to really evaluate this on a known field, I would say. Okay, so sorry. So the hello, hi. So in order to cover the defects, the bridge and open defects, so we used a flow provided by Siemens, by Nicola, and presented by Andreas. A very nice presentation, by the way. And we have a lot of the flow is actually easily integrated, integrated in our usual flow, in ATPG flow. You're gonna see a lot of code, but please don't be afraid. It's just it's just presenting the flow, and you will see it's pretty easy to implement. It's really efficient. The only difference with the flow that we use for scan, TF, transition fault, and stochastic pattern generation is that this solution wouldn't be possible to be implemented early in the product development. You would need to implement it, once you have the layout netlist. So obviously it's not going to be really at the start of the project. So the first step would be the layout database generation, because you would need the layout netlist, like a database, layout database, in order to identify physically where the bridge could be and the open defects could be, actually. And for that, you use like a full dictionary that you would generate as well, based on the layout database, and using the Mentor, the Siemens solution, to generate a UDFM file. And this file will contain all of your defects, like the identified defects on the layout database, the first one that you've generated previously. The flat model that you will use is going to be the same that you've generated for your from your ATPG flow. So it's going to be the one that you use for stochastic, for TF, so. And then the UDFM that you will generate, which is kind of a full dictionary, is going to be an input to your ATPG in order to generate now the patterns that are going to be in charge of covering those faults, those defects inside of the chip. So once you give this this as an input to your ATPG, you will be able to generate the patterns, and be able also to. The difference with TF and stochastic is that in TF and stochastic is that you can evaluate the coverage. You can target a certain coverage. Here it's a bit different, because we are talking about critical area and total critical area. So you can the target really is the critical area, which means basically the most probable, the highest probability of having the defect would be the highest total critical area of any defect that you would see, bridge, open, or static bridge. Okay. So, and what's really interesting with this flow is that you can see the gain, the coverage gain, actually, that you've had just by adding those patterns compared to what you would have only with TF stochastic. So you can report, so what you see here, report statistic and the critical area, and then you generate the patterns, the new patterns, using you would read your usual patterns. So it would be transition faults for delay and stochastic for static, and then you would insert your patterns. You would generate the new patterns that are the bridge defects pattern. So it could be delay for bridge delay and open, and static for bridge static. And then after that, you would have the analysis of the coverage and of the critical area coverage, the gain on the coverage compared to previously what you had just with TF stochastic and without the new patterns. Okay. And you have really many options to use. I don't know them yet at all. Not all of them, sorry, yet. But the most interesting is the order patterns based on critical area. Why I'm saying that? Because it's the same behavior that we have in TF. In transition, when you generate transition patterns, you tend to generate a lot of them if you target a certain coverage, right? Here, it's exactly the same. You would generate a huge amount of patterns, but to reduce test time, because we don't want to spend too much time on this, you can reorder them based on the critical area, and you would then cut off, you know, the last ones, because you would decide that the ones in the beginning, so the first patterns that have the highest critical area, are the most important, relevant to keep. It's exactly the same that what we do actually on transition fault. Okay. So now we're going to move to the generated data that we have once we generated the patterns. You need to know also that it's possible to generate a single or a top-off flow. The top-off flow is the most interesting for us because we want to generate the patterns on top of what we already have as patterns. So in addition of the TF, you're going to add on top of the TF, you're going to add delay and open. In addition of the staccato, you're going to add static, bridge static. Okay, so we've decided to test all of them. So we've generated the three sets of pattern, and here we have a few numbers, quite interesting. So the gain that I was talking about is that for the bridge static, we took the staccato that we use on tester, that we really use on our chip for our target coverage in imaging. And then we computed the gain, which is 1.33%, which is added, the coverage is added by those new static bridge patterns. And then the bridge delay is the most interesting for us because it has an addition of 13% compared to the transition. So at speed testing, you would have 13% coverage, and it's quite huge. But you will tell me, oh my God, the number of patterns is quite huge as well. But as I told you previously, I can show you if you're interested the exact numbers. But the 27K patterns that we've generated on bridge delay, we've actually have maybe 8,000 that we have the highest coverage in TCA. You see 71%, you would have 66% around 8,000 patterns, and the others are adding a bit and a bit to target 71.72 coverage. So we could decide this the same way than what we do for transition fault, is that, okay, we want between, you know, the test time and the coverage, maybe 66 is fine, maybe 8,000 patterns instead of 27 is fine. So, and that would be possible by just cutting off, because you would already order your patterns, right? Okay, and now we had a few tests on wafers and like several wafers. Okay, so the first results on our first trials were really not promising because we had a lot of fails, like really a lot. But after a first diagnosis, we realized that most of the fails are recurrent and were, you know, due to an understood issue. Actually, it's just from a static register. So I've decided to ignore the just few cycles that were failing, and we dropped to 3% fail, and we did the tests on several wafers. So we have data on a few thousands, a few dozens of thousands dies, but obviously we target much more than that, hopefully in the next weeks. And so after that, when we masked the few cycles, we've decided to run it on the wafers again, and we've had quite interesting results that we will see on the next slide. But as you can see already here on the wafer, it's really not located in the same area. So it's really interesting information here, because it's the fails are in white, by the way, sorry, and they are located all over the wafer. Okay. So we collected actually the fails on a few parts, on like a lot of parts actually, and then we've decided to compare like the three fails on wafers to see if they are within the same range, and we were not really surprised by the result. But the most interesting was to compare them actually, like to compare what is comparable, right? So we compared the bridge static with staccato and chain test. You will tell me, oh my God, it's it's too high compared to the STCAT. But please keep in mind that the STCAT is already an add-on to the chain test. So what we would compare is that the chain plus the STCAT with the bridge static. And what we've noticed actually is that the coverage is relevant because all of the failing dies within the bridge static, most of them are fail as well in STCAT or in chain. But we had only 2 dies actually that were failing only in bridge static and never fail in any other mode. So that means that we caught at least 2 dies on 10K. So 2 on 10K, it's 200 ppm, right? So it's quite interesting. And then we compared also the bridge delay results, the fail results on and open compared to our TF, transition fault. The same again, TF here, I represented the chain test only on Venom, but keep in mind that it's an add-on, okay? So when we compare them, the open and the bridge delay are a bit higher than TF actually. Maybe too high for what we target, but after diagnosis, we understand it a bit more. So the thing is that on 10K dies, we have 35 dies that are failing only on bridge delay. That means that we don't catch those fails in any other test, okay? Chain, STCAT, TF, functional, we don't catch those fails. Now, 35 is quite huge for our sensor. That means it's 3,500 ppm, so it's still high. So what we did was that, okay, and I will go back later on. Sorry. So what we did was that we decided to collect all of the logs of those 35 per 10K, every 10K dies, mental logs, and to analyze them and to run some diagnosis. So what we've noticed is very interesting. It's that most of the fails that we've seen are recurrent. And one of them occurs only once, like 1 die on 10K dies. That's the most interesting part. Because with bridge delay now, the point is to understand is if in the 35, the defects that you actually caught are relevant. It's the relevancy of those defects. Is it relevant to keep the 35 and to go up to 3,500 ppm? Of course not. But what we can do is that with a much, if we push the diagnosis, we would be able to see maybe the recurrence, because with the diagnosis that we already did for the recurrent fails, it wasn't concluent. Unfortunately, we had too many suspects, but we've decided to push it a bit farther to see if we keep the 35 or if we just consider that those 35 are not relevant, but at least we have 1. And this is the most important one that you cut with this and not with any other test. And this is very interesting for us, for what we want to do. And then I go back, sorry, for the open delay. For the open delay, we had 9 dies on 10K that were failing, and among which 6 are not caught anywhere. So 6 is still high for us. But as the same strategy for bridge delay, it's gonna be the relevancy of the fail, because you could have the pattern is too efficient, it catches the even a minor defect, which wouldn't be impacting the functionality, right? So our next steps would be to take those 35 parts and to maybe analyze them in fiability and to determine if those 35 are really rejected dies and are really failing dies, or if we can ignore the 34 because it's recurrent and it's an understood issue and it's not impacting any functionality of the die, and we would keep 1 because this one is the most important for us, okay? In the next weeks, we target really, hopefully, to run the same patterns on 100K dies on the same sensor and have much more data. And we also tried a bit of layout diagnosis. But as we need a license for everything, we didn't manage to see the result yet, but it's gonna come in the in the next weeks, hopefully. But I think for now, what we can say is that the test cost, the test time is that was too long, could be easily reduced, as I told you, only on the bridge delay arm, because on the stochastic, it's in the static, it's pretty short. So we could reduce that by reordering the pattern and just cutting off the most, the least relevant ones. The diagnosis, the further diagnosis, because we absolutely need to determine if we keep the 35 and the 6 in open delay, the 6 failing dies, or if we can refine a bit more. And what's absolutely amazing with this flow is that in the beginning, you would, at the generation actually, you have many filters that you could use, okay, to refine your analysis and generate maybe based on a distance to determine the bridge, to calculate the bridge, maybe a shorter distance, a longer distance, and all of those we didn't have the time to try everything, obviously, but you have many options, many filters that you could use to refine a bit more, because on TF and STUCAT we have many years of experience, and this is new to us, so we didn't try everything obviously. But in conclusion, I would say that this solution is very interesting, especially in automotive products, because if we could target 100 to 200 ppm, which means the 2 dies that we saw, for example, in static, and maybe the 1 die that we saw in bridge delay, this would be a huge addition for us and for our automotive customers. So thank you for listening to me, and if you have any question, please feel free to ask. Thank you. Thank you.